So good morning to everybody. This is the webinar that is organized by Life ANHIDRA and Life POLITEX in the frame of the 2025 EU Green Week. As you know, the Green Week also invites some partners and some initiatives to perform some parallel session together with the official channel that are released in Brussels regarding the EU Green Week. And regarding ANHIDRA, this is the second year we are participating in this kind of event. Last year, the main theme of the EU Green Week was water resiliency, and this year the main topic is about circularity. It's about circular economy. As you know, is now it's bringing a pivotal moment in the European Union about the green transition. So as part of the Green Week, which is themed about circular solutions for a competitive Europe, we are joining this webinar together with 9 European funded projects that are already working on circularity based on different topics and different materials and strategies. Our webinar is divided in three different sessions. The first one will include 4 projects and will focus on circular economy, recycling, reuse, and reduce, about the possibilities to valorize and reuse different kinds of materials, mainly polymers for thermoplastic, thermosetting, and applications. The second part of the webinar will focus on industrial urban symbiosis in order to explore different initiatives about collaboration of different industrial sectors in order to take profit from different waste streams, and considering this kind of waste streams as raw materials for different applications and different sectors. And we'll close the seminar with the third part of this webinar that will focus on valorization of waste streams to obtain energy and other kind of resources. So this is a short introduction about the webinar, about the main themes that we want to explore. I hope all of you enjoy, and we will start the presentations with the first session about circular economy, and the first project we want to release here today. This project is Life POLITEX. It's a project that is coordinated by ITEX. The title of the presentation will be the fiber-to-fiber full circularity in the textile sector through novel polyester recycling technologies, and will be presented by Concha Silvestre. So Concha, the floor is yours, please.
Hello, good morning, everyone. Thank you for attending this webinar. And I will start now. Well, okay. So as my workmate Oscar says, I'm Concha Silvestre from ITEX. I work in the Technical Fibers and Textile Materials Department, and today I'm presenting Life POLITEX, a project aimed at achieving full circularity, fiber to fiber, in the textile industry. Life POLITEX and 2 affiliated entities. Coordinator, Coleo is one of the beneficiaries, with Wastex as their affiliated partner, selling sport to Europe, and are both key beneficiaries. Circular economy initiatives and waste reduction. Can you hear me? Better? This project is funded by the European Union under the LIFE program, which supports circular economy initiatives and waste reduction. This project operates across Spain, Italy, 60% of which is co-funded by the European Commission. It has a total duration of 42 months, 3 years and a half, and it kicked off in June 2024. So we are already 1 year in. The problem: the textile industry still follows a linear model with a significant environmental impact. In 2020, it consumed 93 billion cubic meters of water and emitted 1.7 billion tons of CO2 per year. Only 22% of textile waste is recycled, while the rest, 78% of textile, was releasing around 1 million microfibers into the oceans and generating 92 million tons of waste. There is a growing need for change. A recent survey of 50 fashion brands show that 80% of them intend to produce recycled polyester from plastic bottles. In most low-value products, such as rags, insulation, or filling material. Textile products. Several strategies have been tested to address this issue, such as reuse or redesign, recovery. However, no one of these approaches have been proven fully effective when it focuses on the industrial implementation of chemical methods to reach textile waste. Like POLITEX is the first market-oriented project aiming to demonstrate the viability of polyester recycling for the true circularity. Of high-purity polyester recycling. We are working with 4,500 tons of textile waste per year at the Coleo plant. Of this amount, 1,500 of which will be recycled either mechanically or chemically, although this is not in the scope of the project. This is the K fraction targeted by the project, and the rest will be non-cotton, non-polyester fibers. Will also follow outside the scope of this project, but will be recycled through mechanical recycling, pyrolysis, or hydrothermal processes. The main 1,750 plan, where they will first undergo the polymerization to produce high-purity BHCT. This BHCT will then be repolymerized to obtain polyester recycled from textile waste. The recycled polyester will be processed by ANTEX to produce 550 tons of recycled yarn by the end of the project. Okay, this diagram illustrates the chemical recycling process of textile waste containing more than 90% of polyester. Have more than 90% of polyester. Threading. The textile waste is mechanically readied into smaller pieces, agglomeration. The red material is agglomerated to prepare it for chemical processing. And then the polymerization, where the PET is broken down into its monomer components. Contaminants are removed to yield purified monomers. Then we move to the polymerization. The purified monomers are repolymerized to form new polyester. So at the end, we obtain polyester which has some achieving the high purity of this polyester. These closed-loop recycling methods allow PET textiles to be continuously reused, significantly reducing plastic waste. Although chemical recycling of PET represents a major opportunity for circularity in the textile sector, there are still several in order to ensure its viability at the industrial scale. Challenges as complexity of post-consumer textile waste. Textile waste is often made of fiber blends such as cotton polyester, dyes, chemical finishes, and contaminants like buttons, zippers, labels. This heterogeneity makes sorting and the polymerization process more difficult. Other challenges will be the efficiency of the depolymerization process. Producing high-purity PET from textile waste requires optimized and controlled process conditions, especially when the PET is degraded due to the previous use or treatments. Cost and energy consumption. While chemical recycling enables the recovery of high-quality monomers, recycling efficiency and ensuring industrial scalability is crucial. Recycled PET quality assurance. To successfully reintroduce recycled PET into demanding textile applications such as yarn production, it must meet strict standards in terms of purity, viscosity, thermal stability. Reaching a quality comparable to virgin PET is a challenge, but it is the core goal of the project. And current scale limitation. Many chemical scaling up to full industrial levels require further investment and technological fine-tuning. However, addressed through advanced separation technology process for real textile waste, collaboration between industrial players with expertise in recycling, polymers, and textiles, and an approach that prioritizes economic and environmental viability, not just technical feasibility. Well, what we expect to achieve at the end of the project. By the end of the project, in addition to achieving a circular recycling system for polyester-rich textile waste, we also expect to recycle 4,500 tons of textile waste annually, including these 1,755 tons per year of the polyester-rich fraction, reduce greenhouse gas emissions, avoiding the release of 915 tons of CO2 into the atmosphere, improve circularity by reintroducing these 550 tons of recycled polyester each year into the textile value chain, scale up chemical recycling to an industrial level, and also ensure that the recycled polyester reaches a high purity level, around 90%, to be as similar as possible to the virgin one. Well, our legacy. At Life POLITEX, our aim is not only to develop an innovative solution, and adaptable to other contexts. With that in mind, we are working along is planned with an initial implementation in northern Italy by 2031. We also aim to reduce capex by 20%, making the initial investment for this technology much more affordable and encouraging adoption by other companies. And increasing textile enabling the process to scale up a larger columns of material to be managed. Another important goal is the transferability of the Life POLITEX solution to other industrial sectors as the automotive one or the food packaging industry, which will significantly expand its impact beyond textiles. All of this is done while maintaining the three case elements: circularity, flexibility, and techno-economic efficiency. And of course, always with a lower environmental footprint, which is one of the main objectives of the project. In short, Life POLITEX is not just a technical proposal, but a transformative solution designed to be replicated, scaled, and adapted to different settings. Production model. Well, if you would like to see more information about this project, here you have several links. Our link to ITEX, to the ITEX website, also the European Commission website, and here there are also our profiles of X, also known as Twitter, and LinkedIn. So thank you so much for your attention. And
Hey, Concha, thank you very much for your nice presentation. Sorry for the audience for this technical problems we have experienced partly about sound, but I think it was so clear about the novel technologies for recycling the polyester, not based on mechanically but on chemical methods in order to take profit from a textile to textile point of view recycling process. So now we are going to move forward to the second presentation, also focusing on polymers and plastics. In this case, we're going to focus on bio-based alternatives for packaging. So the presentation will be held by Pablo Lopez from ITEX, and the title of the presentation is Viable, Safe and Sustainable PHB Value Chain for Food Packaging Applications. Is this project. So Pablo, the floor is yours. Thank you for attending the webinar.
Thanks to you, Oscar, for the nice introduction. Also, special thanks to ANHIDRA Life Politics Project for inviting us, me, and on this project to this webinar, to have the opportunity to share with all of you what is the project about, and also to share common points of view and common interest. Okay, so the project name is Viable, Safe and Sustainable PHBB Value Chains for Food Packaging Applications. Is started back on September 2023, will end in August 2027. The consortium consists of 15 partners from United Kingdom, Belgium, Spain, mainly Finland, Netherlands and Italy, and integrates from academia, universities, research centers to final end users. There you have both links to the project websites and also to the LinkedIn profile, but in the end you will also have the other social media that we have available for you to gather more information and to connect with us if you are interested in something the project is about. So what is these purposes as project? Well, it's the need to replace and to find an alternative to food packaging products that are, of course, based on polymers, fossil-based materials. So the critical issue we have, and every technology have with with fossil-based polymers, is that the end of life usually results in residues that pollutes the environment because they don't biodegrade by themselves. If they are not recycled, they don't have any use, or if you don't find any other solutions, then they remain for hundreds of years, right? So that's why biopolymers comes as a strong alternative to these fossil-based materials, because they are either bio-based, either biodegradable, or both. Then within these biopolymers, we found the PHAs that are 100% biodegradable and also are synthesized by microorganisms from renewable carbon source. So we have like a wide range of things or components we can use to feed these bacteria, these microorganisms to produce the PHAs. And then we have a specific brand of polymer of PHA that is the PHBB, that it also adds suitable properties for these food packaging applications. So then we have a candidate here to be a replacement for these mainly polyolefins that are the ones that are used in food packaging applications. Then, as everything in life, it has their pros and cons. The advantages is that we have already mentioned, the biodegradability possibility, and then having some mechanical properties that can be more or less compared with the ones made by fossil-based polymers. But on the other hand, we have high-cost feedstocks. Then we also have, specifically for PHBB, a poor processability in main extrusion technologies due to a slow nucleation rate that can come even after days or weeks. And also something that is very critical for food packaging, that is a lack of flexibility and also poor recyclability related with being high sensitive to temperature and shear. That's why BIS propose different solutions to these disadvantages, as use agri-food industry waste streams as carbon, nitrogen, and phosphorus source as a feedstock to replace these high-cost streams. Also, to tackle this poor processability, this nucleation rate, to find for non-hazardous certified additives that they don't hinder this biodegradability, that they don't make that the final polymer has any impact on the environment. And also to fix or to balance out this lack of flexibility, to design different PHBB blends to reach an optimal mechanical properties. All of these supported by an SSBD framework, so safe and sustainable by design. That's the main point of this, is to try to not decrease, to not hinder, to not modify this biodegradability, this compatibility with the environment, by looking for solutions that are within a safe and sustainable framework. Then this is what we that we pose our suggestion as a value circle, a value change of this. Then we have the food industry that use or produce these waste streams. In our cases, in this project, what the streams that we have selected and the ones used in candy industry, sugar, specifically, and then further supports to the poultry waste stream as a sources of carbon, nitrogen, and phosphorus to feed and to produce the PHBB. Then biotechnological routes that produce both the precursors and also the extractions within, again, this safe and sustainable framework. So we want to use low intensity consumption of energy, of to not use solvents that, for example, has a high impact into the environment, and to use and always to have to have the best yield in terms of production of PHBB. Then the final range of polymer with a high free hydroxyvalerate content, that is the one that give this flexibility to the polymer. That's why we can modify also through the blends. That is the next step, this content of valerate. Also, again, the bio additives, all the formulations, again, with the safe and sustainable framework. And then to convert these master batches with the additive and the BIS PHBB through conventional technologies to produce films, to produce just to then knitted mesh bags, and also thermoform trays. And then in the end, what we have is this packaging that will be used again by the food industry. And we will not have any left residue in the end. That's the idea. That's where we close. And also it can be used again to feed. That's one of the, is not pictured here, but during our work, what we have also seen as that these residues can be also reconducted to the roots, to the fermentation points, to even feed further the bacteria. So the project roadmap right now looks something like this. We have the process optimization and the setup of a pilot plan, of a demo pilot plan to produce this polymer, the BIS PHBB. So we have the optimization of the waste streams, their characterization, and to know how to treat it to fully obtain yield the most high carbon, nitrogen, and phosphorus content in them. Also, the selection of a microorganism that yields the PHB with the highest hydroxyvalerate possible, and also to produce or use a non-costly volatile fatty acids precursors that are the two flows, the two streams that are using in fermentation to produce the PHBB, and also to design an innovative green process to extract this PHBB. Then we will have the second step, the middle step, that will be the additives and component optimization, that will be 3D and characterization of the different components, different additives that can be used into that can be added into the PHBB to modify this nucleation rate, and also to characterize and to analyze how they impact and how they modify this PHBB, and then a study to optimize and yield the best mechanical properties in the end. And as a last step will be the prototype, will be the validation and transformation of this polymer, the BIS PHBB. So the rotation, again, as I have mentioned before, the rotation of thermoformed trays, films, little bags for the food, for food packaging applications, both pilot and industrial scale. And with those prototypes, with those products, to conduct an analysis of end-of-life scenarios, basically to assess their recyclability, the possibilities that they can offer in late stages of their use, and also to know or to assess, to validate these the biodegradation routes in the end, where the recyclability is not positive, or the results are not on the point where are really justified to be choose. So again, I have repeated in several times, but that's why it's very core to this. that is this safe and sustainable by design, but not only at the technical level, also to conduct it, to carry it out, even at social and economical level, to ensure that this that the PHBB, the material has like a complete validation in the full value chain from from the academia to the industry and including the decision makers and the citizens, consumers. So where we consider uh, all the actors that are involved in the bees value chains, is important for us to assess that we are not leaving out any critical point that can be an issue in the further future. So to wrap up, just what are our respective project results. So the production of a sustainable PHBB with a high content on this hydroxy valerate, and especially using the, residues as feedstocks. So we are closing the loop with the production of this polymer. Then having a formulation that is suitable for semi-flexible food packaging applications, and then to demonstrate, to assess the biodegradability and also the mechanical recyclability. Why to assess this biodegradability? Maybe you are wondering why, because that's a way of demonstrate that the selection of the additives had not hindered the final result of this key property of the PHB, because it will defeat the purpose if we use something to be able to reach the requirements of semi-flexible food packaging application if we then not achieve biodegradability by adding this type of modifications. And especially again, maybe I'm repeating too much, but it's important for us is these value chains, the adoption of a value chain under a safe and sustainable by design framework. Then the project outcomes measures, so with the reduction of CO2 emissions in more than 50% per kilogram of polymer compared with the fossil-based counterparts. The contribution to circularity by using these waste streams as feedstocks. So in total, close to 300 kilotons of biomass, and also to use less toxicity materials, so avoiding a total of at least 2,200 tons of hazardous substances. And of course, again, that's an outcome from the this value chain, to including the value chains. The social level is to enhance the consumer awareness of what is the impact of these kind of products. So it's important to also have a technical solution, but something that can be be adapted by the final consumer. So just for the end, to give you thanks everyone for the attention. There you have also our contact for the BIS project, and on the right side you have our website or LinkedIn profile. We also have a YouTube account and a Facebook one, where you can find from videos to then more infographics about the project, and to be aware of the latest news about the program. So thanks everyone again.
Thank you very much, Pablo, for your presentation and showing how are you working with some bio-based materials, even mainly coming from a microorganism or even so with sugar derivatives and so on. So for the next presentation, I will suggest a short change in the agenda to the time availability of one of the speakers. It was expected now to present Ivan Domenech from ITEX and the Live Biocom project, but for the colleagues from IDIME, and if Angel Marcos is ready, I will kindly ask to present the from their side in order to reach your time. So, Angel, if you are ready.
Yeah, thank you, Oscar. Thank you. I appreciate it. So I'm going to share my screen. Okay. Are you seeing my presentation?
Yeah, now it's in full screen. Thank you.
Okay, perfect. Okay. Okay, well, thank you all for your attention. So my name is Angel Marcos. I work at the Process Management and Sustainability Department in IDIME. And today I'm presenting our project CIRSYST, called Circular Systemic Solution for Plastic Packaging, Bio-Waste and Water, which is funded by European Union in the framework of the Circular Cities and Regions Initiative. So just a quick overview over our project and the key numbers. As you can see, we are a partnership of over 32 partners in 9 different countries. And we are working on circular economy in 3 research areas, water, bio-waste, and packaging waste. We started in June 2024, so we are kind of close to the deadline of the 2018 month. And we have a total budget of nearly 11.5 million euros, which counts with a contribution of the European Union of nearly 10 million euros. Our duration is of 36 months, so we are kind of happy with how we are going right now at this moment. You can see here the partnership. We are really different areas of Europe involved in the project. We have different demonstrators in Spain, also in Belgium, Sweden, Finland, Slovenia, Hungary, and Greece, and also a partner in the United Kingdom. And which is kind of interesting of this project is that, leaving aside that we are different countries involved, most of the partners are part of the Circular Cities and Regions Initiative, which allow us to integrate this spirit of cooperation that is behind this initiative to enhance circular economy from our different perspectives and the different research areas that we are working in. So going deep into the project, our main objective is to contribute to catalyzing the transition towards a sustainable circular economy through what we have called the circular systemic solutions. So CIRSYST presents a series of shared demonstration experiences of new technological and societal adaptations to a circular economy involving 8 European regions. And the project focuses on 3 of the priority value chains of the circular economy plan: water management, bio-waste, and plastics and packaging, as well as in the potential synergies among them, which is kind of important. We do not only want to be able to demonstrate these circular systemic solutions, but also to see how these solutions can interact between them and see the different synergies between them. In that sense, as you can see on the screen, we have 9 different demonstrators. Demonstrator 1 to 4 are focused on water. I will explain later demonstrator 1, which is the one IDIME is leading. Demonstrator 5 and 6 revolve around bio-waste, and demonstrators 7 to 9 are about plastic waste and packaging in the food industry. So with the yellow lines, you can see there are synergies not only between the demonstrators in the same research area, but also between demonstrators that are focused on different research areas, which allow us to get to a higher impact during our project. It's also important to understand that our aim is not only to be able to demonstrate these different pilots, but also to prepare these guidelines, deep guidelines that allow other regions to deploy our circular systemic solutions and to enhance circular economy through them. So we are also assessing the replicability of the demonstrators, the barriers and the drivers that can allow these demonstrators to be truly implemented all around Europe or other regions around the world. So I'm going to explain demo 1, which is the one IDIME is leading. IDIME leads work package 2, which is the work package focused on water. We are interacting with different partners that are also working in the water reusage for different uses. In our case, we are applying wastewater or treated wastewater into industrial uses. And our main objective is to develop a symbiosis model by using reclaimed water to meet industrial and urban water demands like street cleaning, park irrigation, or firefighting. Specifically, we will apply low-cost tertiary treatment, including rainwater, to obtain different sources of reclaimed water. And we will develop an AI-supported water mixer where water sources can be adequately mixed to meet water demands in terms of quality. And we will also develop an intelligent water management system to supply reclaimed water according to the demand. So I think it would be better understood in this diagram. As you can see, demo 1 is designed to demonstrate circularity and symbiosis in water in a complex scenario. And it will be carried out in an industrial park where a wide range of water demands, both industrial and urban, will be covered by reclaimed water, and that will be managed by AI. So, as you can see in the diagram, we have the industrial park, which provides with wastewater to the wastewater treatment plants. And in that wastewater treatment plant, we will install the tertiary treatment that will allow us to obtain different water qualities, adapting that treatment to the different needs of the companies. So, by installing sensors in both the industrial park and the wastewater treatment plant, we will be able to match these needs or these demands with the different water qualities that we are producing through a water management intelligence system that will be based in artificial intelligence. So the idea is to be able to produce, or in a more efficient way, the different qualities that will be actually needed in the companies in real time. This is a more detailed diagram of the water treatment. We will be applying a disinfection, a microfiltration, activated carbon, nanofiltration, and reverse osmosis. Not all the treatments are necessarily applied to water, depending on the water qualities that we want to obtain. So depending on the needs of the companies that are being measured and seen through this intelligence system, we will apply more or less treatments in order to obtain these water qualities that are actually needed. As you can see, the location and geographic scope is quite important for us regarding these barriers and drivers that I was speaking about before. We are working in Ribarroja del Turia, which is like 20 kilometers from Valencia, and the current wastewater treatment plant actually, or currently collects wastewater from sectors 12 and 13 of this industrial area. We are talking about a wastewater treatment plant that is really integrated into the industrial area. And this is the key driver for our demonstrator. I mean, what is really important to be able to deploy this system is to have these synergies between the industrial areas and the wastewater treatment plant in order to collect the water and be efficient when giving that water back to the companies. I would also like to mention our partners in this specific demonstrator, not only in the project. So we are in charge of the basic design, commissioning, assembly, management, and monitoring of the demonstration plant, also of the sensorization of demands. But we also come with the help of Aquatech, will be sensoring the wastewater treatment plant, Hidraqua, which will manage and monitor the wastewater treatment plant, and the Ribarroja City Council that will manage the clean water for non-industrial applications, and has also helped us to engage with companies close to the wastewater treatment plant. Regarding the stakeholders that are also really important for us, we count with the companies that are close to this treatment plant in the industrial park, more than or nearly 500 companies. Also EPSAR, which is the administrative entity that actually owns the wastewater treatment plant. And finally, the different engineering companies that will detail the engineering, construct, and install the demonstrator. So, well, I think I've been kind of quick, but probably better for all of us. Thank you, everyone, for your attention. If you have any doubt, any comment, or want to know more about the project, just send an email to me. You can look up for us in LinkedIn, and also we have a webpage. So please feel free to ask or comment whatever you obtain it. And thank you very much.
Thank you, Angel. Thank you very much for your presentation and showing how this kind of projects and how now wastewater treatment plants are not only focused on water treatment stop the task, but also recovering some resources and to reuse water, producing different qualities, and so on. So it's a very nice example about this kind of also industrial symbiosis between different processes. So for closing this session 1 of our webinar, now is time to present our Light Biocom project that will be introduced by Ivan Domenech from ITEX. So in a previous presentation, we focus on thermoplastic materials and polymers. Now, we could also explore how to recycle and to reuse some wastes coming even from thermostatic materials. So, Ivan, the floor is yours, please.
Many thanks, Oscar, for your presentation, and thanks for the organization to give us the opportunity to show our developments in the project. Please let me just share my screen. Okay, Light Biocom project, it's a project related to the new bio-based and sustainable raw materials enabling the circular value chains of high-performance lightweight biocomposites. Okay, the project is a consortium coordinated by ITEX, and our Light Biocom project brings together a multidisciplinary consortium consisting of 15 project members, not only from research and academia, as well as from the industrial partners like the automotive, aeronautic, and construction sector in order to validate environmental relevant demonstrator in the project. This project is across 4 European countries like Spain, Italy, Netherlands, and Germany, and one associated European Union country as United Kingdom. This project starts in the year 2023 and has a 44 months of duration and a 4.2 million funding euros. This project are in the research innovation action in the cluster 4 of the call 2023. And this project applies a multidisciplinary approach to develop a new sustainable, cost-effective, and energy-efficient lightweight high-performance composites. All of this with inherent recycling properties in combination with novel efficient processing and recycling technologies. The main development areas of this project are in 3 topics mainly. The first one is the materials. The second one is the production technologies, and the last one is a transversal development area in order to develop different methods and tools in order to transfer this knowledge to the final industrial sector. To better understand these areas, I'm going to explain before. And about the expected outcomes, there are 2 main topics in this project. The first one is related to the material and the processing results in order to develop 3 types of advanced bio-based resin compounds, thermoset mainly. The second one is mainly focusing to develop a new additives based in biomass-derived nanofillers, and also to combine this formulation of the bio-based resin and the nanofillers in the final formulation of the resins, including all of this. On the other hand, there are 3 different sustainable textile products in order to incorporate recycled fibers or recyclable fiber in the high-performance components and structures for the composites, and also to combine the bio-based types of these resins and the sustainable textiles in different components for the lightweight composites. And another important topic of the project is to develop a new fast curing technologies in order to improve the cost-effective of the composites. On the other hand, about the sustainability results, the results are focused on the new recycling technologies for this kind of materials, and also to develop holistic optimization tools in order to develop and design in the future a new sustainable composite structures and without the modeling and the validation processes. In the case of the material, the basis of all Light Biocom project results is the development of new raw materials that reduce mainly the cost and the waste, while introducing a recyclability and sustainability into the resulting high-performance composites in this sector. In this regard, the new composite materials will be developed and studied in three main areas. The first one is to develop a bioresin with a covalent and adaptable networks in order to good or better recyclability in this kind of materials, to develop a bio-based additives based in enzymatic and nanofillers from the nature, and also to incorporate in a new intermediate textile products recycled and or sustainable fiber like these ones. In the case of the production technologies, there are two main topics. The first one is the material processing into intermediates, components, and structures. And in this area, we are developing a new intermediate prepex with the new formulation suitable for producing sustainable prepex and to incorporate in at industrial scale. The other one is to develop a new intermediate materials like honeycombs with a technology to enable the transformation of the non-woven textiles into a honeycomb material, resulting in a more sustainable high-performance component. All of this with a novel manufacturing technologies. And the last one is to develop structures based on textile reinforced composites with the hand of the two new patents in order to replace the conventional materials such as steel, aluminum, and concrete, in order to introduce new fibers like recycled carbon fiber and recycled glass fiber into robins, jars, fabrics, and nonwovens. And in the case of the innovations in the production process, the projects are developing at this moment a new fast curing technologies in order to reduce the cost, the times, and the temperature of this kind of processing the materials. The first one is a resin transfer molding with a frontal photopolymerization in order to reduce the temperature and the time of this process. And the second is a microwave-assisted vacuum infusion in order to reduce the quantity of the materials needed for obtaining these composites. In the case of the transversal work package about the methods and the tools, there are several works related. And in this case, the first one is a holistic optimization framework for sustainable design of composite structures in order to develop a complete ecological optimization tool to incorporate in the future at industrial scale in order to design and develop a new composites, keeping in mind the cost, the sustainability, and the recyclability at the end of the life. One another important topic in this project is to study the recycling methodologies from the developed materials and the current ones. And in this case, we are studying different chemical recycling processes and solutions, such as epoxydolysis and solvolysis, for sure, using an appropriate biological solvents and supercritical fluids with a lower environmental impact. These techniques could provide a better separation performance, enabling the recyclability on the one hand from the resin, and on the other hand, the reinforced fibers in order to reincorporate and reuse in another one's materials. You could see in the screen several examples. The first one is dynamite fibers. These fibers are from end-of-life ballistic combat helmets, and they are introduced in a new jars in order to use new robins for pull-through profiles. And also, another example in the project is the reevaluation of the carbon fiber from the end-of-life composites, mainly for the aeronautic and automotive sector, in order to reintroduce this fiber in a non-woven yarns and fabrics for obtaining a new composite. About the chemical recycling, this project are focused to develop and incorporate at industrial scale different techniques like atmospheric pressure extractor, high pressure, and microwave assist extractor. All of this, we need to keep in mind that it's very important to assure that all these developments are with a lower impact in the project. And for this reason, we are doing a life cycle assessment cradle to cradle in order to verify from an environmental point of view that this composite developed in the project give an advantage against the current state of art and the current materials. All of this considering the different raw materials, resins, fibers, and intermediate, as well as the curing technologies and also the recycling processes in order to reincorporate these materials another time in the composite sector. And finally, all of these are being validated at this moment with 4 demonstrators in an industrial relevant scale. The first one is related to the automotive sector industry with 2 use cases. The first one is to a spoiler for a sportive car in order to change the current material like epoxy resin and carbon fiber with natural fibers and biogas resins. And the second one is in order to develop a new tram floor in order to change a polyurethane cardboard and a blend of materials with a newest honeycomb monomaterial. The second use case is related to infrastructure sector in order to develop a new tunnel lining in order to change the current materials like glass fiber and epoxy resin for more sustainable ones. And finally, the most ambitious use case is the aeronautic demonstrator in order to obtain a new leading edge for a plane for develop a new material with lightweight properties and more recyclability. And this is all for my side. Many thanks for your attention. In this slide, you can show our social media and our contacts in order to get more information. Thank you.
Thank you very much, Ivan, for the nice presentation and show which are now the main novel technologies for recycling and reducing some wastes coming from complex materials like thermosets that 20, 25 years ago were very difficult to recycle and to reuse. So now we will go forward with the second session of the webinar. Now we are going to start with the industrial and urban symbiosis. And the first presentation will be released by Jorge Arroyo from CIRCE, researching entity in Aragon in Spain. It is going to present Aragon's regional hub for circularity and the demonstration of local industrial urban symbiosis initiatives through the REDOL project. So, Jorge, the floor is yours, and thank you for attending.
Thank you, Oscar. Thank you also for the invitation to this session.
Welcome.
I'm going to share my screen. Okay, as Oscar mentioned, I'm Jorge Arroyo. I am project manager in CIRCE Technology Center. We are a technology center located in Spain, in Zaragoza, and I'm going to present the REDOL project. REDOL is the acronym of Aragon's Regional Hub for Circularity, demonstration of local industrial urban symbiosis initiatives. These are some data about the project. This is the call in which the project was granted in 2022. The project is an innovation action. This means that, as you know, we are making some demonstration and pilots, and we are analyzing the micro replication. The budget of the project is more than 17 million euros, of which 14 are funded by the European Union. We started the project in December 2022, and the project will end on November 2026. As you can see here in the map, we are 35 partners. Most of them are located in Spain and in Aragon, which is the region in blue in the map, in the north of Spain, which is the center of the project. We are working on in a circularity hub in Zaragoza, which is the capital of Aragon, which is the fourth most populated city in Spain. We have also represented 12 European countries with different partners. As you can see here, we are a strong consortium with large companies, small and medium enterprises, technology centers, public institutions, and non-profit organizations. Important to mention that the Zaragoza municipality is also involved in the project. What is the problem we are addressing in Redol. In 2020, each EU citizen generated 500 kilograms per capita, and we just recycle 45% of this solid urban waste. Among others, this is why the European Union released the Circular Economy Action Plan, which fixed some targets for recycling for 2030. For example, they fixed 65% for solid urban waste, 70% in construction and demolition waste, and 75% in packaging. The solution we proposed in the Redol project is the redesign of 5 value chains for solid urban waste in the Aragon area. These value chains are packaging, plastic, construction, demolition waste, textiles, and waste from electric and electronic equipment. And we are working in 5 points. First, we are working in the first part of the project. We work in the data gathering and characterization of the value chain main actors. We are working also in technologies for creating the management and the processing of the solid urban waste. We have also an important part, the development of digital tools for monetization of the optimization of the value chains. We want to make a redesign of these value chains into circular and symbiotic value chains once. And finally, we are working in analyzing the overall impact and with social action and a replication strategy. Finally, the impact we want to contribute to Zaragoza to be a zero residual city for 2040. This will imply that 140,000 tons per year of solid urban waste will be removed from landfill to other recycling activities. From this 90K tons are corresponding to the value chains of the Redol, and this could imply a reduction in the greenhouse gases of 280,000 tons per year and generating an economic activity of 14 billion euros. This is a global view of the project with the methodology. There are a lot of synergies between the different value chains. As you can see here, for each value chain, we are working in 3 main axes. The first one is the management, collection, and classification, in which we are developing mainly machines for sorting based on artificial intelligence and automatization like robotics. With these streams previously sorted, we are working also in processing and recycling new technologies for these waste streams, with the idea to have secondary resources of raw materials which can be used to produce circular products like packaging parts, cement, to reinforce with particle boards, etc. We will see some examples in the next slides. We have also three cities involved as replicator in the project. Each one of these cities have some special interest. For example, Amsterdam has want to support the increase in the recycled beverage of multi-material, multi-layer packaging materials. In Bornholm, in Denmark, they want to learn best practices on the implementation of an urban biorefinery, which is also deployed in Zaragoza, and the establishment of approach in construction and demolition waste, and also in the digitalization activities of the project. And in Prato, in Italy, they are interested in exploring the industrial urban symbiosis potential around the city. Here I wanted to show you some of the results which we are in the project right now. For example, for each value chain, this slide corresponds to the results of the sorting. And for each value chain, we have a machine to sort different materials. In the case of packaging, we have this machine which comprises conveyor belt with it's mobile, and it can be the waste is introduced in the conveyor belt. We have an hyperspectral track camera to classify the paper and no paper and kinds of paper materials, and we have here a Delta robot to sort the materials in different containers. In the case of plastics, we are working in the development of some smart bins, which will be deployed in the city of Zaragoza, in which you introduce the waste, and it classifies according to the color of the container. For the construction and demolition waste, we have also a system based on spectral computer vision and a Delta robot. In this case, the interest of the waste manager is to separate different kinds of material for energy valorization. For textile, you have here the example with this machine will classify the garments by material and by color in different boxes. And finally, for electronic waste, we have this cell in which some PCBs are introduced with computer vision. The different components are detected, and with this small robot, they are automatically removed from the board. In the case of the line of recycling, we will also in the different technologies for each value chain. In the case of packaging, we are working in technologies like delamination, distillation, and compatibilization for multi-layer materials. For the plastics, in this case, there are a lot of synergies between the value chain. So these materials we are using in the value chain from plastics come from other value chains like the construction and demolition. The idea is in composites to remove the fibers and separate the oils and the resins of the fibers. For example, also in the construction and demolition waste, we are working in new formulations of cement. In the textile, we work with PET sources to depolymerize and by glycolysis to obtain PET, recycled PET. And for the electronic waste value chains, we are working in the metal removal with deep effective solvents, making the process, let's say, greener. And that's an example of the circular products we're going to produce. In the case of packaging, we're going to produce polyethylene and polyurethane, for example, recycled, which can be introduced to produce other products like consumer products or automotive. In the case of plastics with the fibers, the idea is to introduce in booth boards to reinforce them. In the case for the construction and demolition, we are working in produce clinker with recycled components. The case of the electronic waste is to extract the materials which are already extracted, but with more efficient and green technologies. And in the case of textile, the idea is to produce high tenacity polyester yarn. Among other activities, we have characterized the value chains and the maker stakeholders in the city. We have worked also in the identification of non-technical barriers for the valorization of solid urban waste among all the partners. If you remember, we are a consortium with waste managers, technology centers, institutions, etc. And we are all working together in these activities. We have mapped also the resources of waste in the city of Zaragoza. We work in the definition of the KPIs and the impact evaluation methodology. And finally, we are developing a platform for data collection and sharing of all the info or relevant info for each value chain. And that's all from my side. Thank you. If you want to know more, you can contact me or follow the Retro project in social network or in the webpage. Thank you.
Thank you very much, Jorge, for your presentation and a good example of how Zaragoza City is also collaborating with other industries, other regions in order to take profit from different waste streams and to reuse not only in own processes but also providing this kind of waste as a raw material for other partners and other processes. So now we are going to show another example of industrial UNC. Yeah.
Oscar, Marco della Feldi speaking.
Yeah, Marco.
Considering that I am in a good position because I'm traveling, can I kindly ask you to show my presentation now? I don't know if I will be the next one.
Yeah, I think it's not a problem.
Thank you very much.
Can you wait for 10 minutes? Okay,
I'm very sorry, Emma. Thanks a lot.
Don't worry. I'm going to share your presentation now, so you could explain about it.
Yes. So I'm going to present the project SIMBA. SIMBA is a coordination and support action coordinated by ENCO. I am Marco della Felde. I'm General Director in ENCO, and I cannot see the slide. Okay, maybe we can move to the next one. Okay, so SIMBA is, yes, thank you very much, it's perfect. Is security local supply chain via the development of new methods to assess the circularity and the symbiosis of the bio-based industrial ecosystem, enhancing the EU competitiveness and resource independence. So the main two objectives of SIMBA, and we will see better later on, is to increase the industrial symbiosis at rural level and increase the circularity of some different materials. If we move to the next slide, please. Regarding SIMBA is a coordination and support action founded under the call Horizon Europe Cluster 6 2023 Circ Bio 017 is a coordination and support action with a lump sum funding scheme. The total budget is, and the total EU contribution is around 1.5 million euro. The starting date is the 1st January 2024 with a project duration of 36 months. The project coordinator is Antonietta Pizza, that unfortunately today is not with us, and this is the reason why I'm here to present the main activities performed. In case for the future you want to be in contact with us, in this slide you can find all the contact details. So moving to the next slide, like you can see, we are 9 partners coming from 5 different countries, and I am happy to see together with us famous partner like Implus or Circe. From Spain, we also have Setaqua. From Belgium, we have involved Centex, Bell, and AUBBP. We have Eclay for Germany. We have from Netherlands, Climate Kick, and from ENCO, we have involved, from Italy, we have involved ENCO and Novamont. Moving to the next slide, please. Okay, here you can find the key objective of SIMBA. The first one is mapping and assessing the current industrial symbiosis methods and approach with the bio-based and not bio-based industry around the EU. The second one is implementing an innovative industrial symbiosis monitoring system throughout the support of the IT tool. The third one is minimizing negative socioeconomic and environmental impacts of industrial products process, improving and optimizing the local supply chain. The next one is supporting local facilitators in the promotion of new bio-based in industrial symbiosis initiative. We have the scope to establish a roadmap for the replication of SIMBA methodology in other regions, also after the end of the project, so we can give a long-term life to our project. We are trying to identify criteria for the selection of specific industrial labs for SIMBA replicability, and we are also accelerating regional, rural, local, urban, and consumer-based transition by developing innovative and sustainable value chain. The last one is involving and coordinate with other existing clusters in the same thematic area. So here you can find the approach that we have defined in SIMBA project. The first step is the knowledge collection and mapping the already existing IS solution. We have classified all of them. We are now developing a new circular symbiosis methodology. We are setting up a criteria for individuating regional lab and defining the regional needs assessment. Once we have done this step, we move to monitoring and validate using also artificial intelligence tools and models. And we will work on the co-creation, cooperation, and knowledge sharing in order to include the highest number of potential end users. Moving to the next slide, please. We can see the SIMBA pilots. In fact, starting from the approach was to define three different pilots, one in agro waste, the other one in food waste, and the third one in wastewater. The partners that we have involved in the validation pilots are Novamont in Italy, BBEPP in Belgium, Implas, Setaqua and Circe in Spain, and again in Belgium, Sentexbel. Like you can see that starting from the different waste stream, we have working and we have trying to extract acid, lactic acid, and PLA in order to reuse this secondary raw material in different industries, and in particular in chemical industry, in textile to obtain fibers, and in plastic to obtain packaging. Another output of our value chain is the biofertilizer that will be reused in the rural area. If you move to the next slide, please. Here you can find also the synergies that we are developing. The first one is the SIMBA Forum cross-exchange with the ongoing project. The second one is the virtual meeting and training section with the Hub for Circularity community. We are developing a training session and interaction with the New European Biohouse community. We are developing synergy and networking with other projects and initiatives. And we are also in contact with social science and humanities integration. Considering that this is a coordination and support action, also the relation with all the other projects is quite relevant. Here you can see the work plan is a little bit different because this is a lump sum. So we have divided the project into two parts, and you can find some twins work package. For example, management and coordination, communication and dissemination. But like you can understand, the central part of our project is in work package 3, where we exploring the existing industrial symbiosis solution. Work package 4, where we define innovative model and industrial symbiosis approaches in the bio-based value chain. And work package 5, where we develop the identification of a high potential industrial symbiosis to demonstrate the SIMBA approach. Moving to the next one, here you can find a couple of slides related with the outcomes. So the main outcomes are an EUP map of current existing IS approaches and methodologies. The second one is an IS monitoring system based on the co-creation approach. We are working to define a database, including the IE tools with all the generated and collected knowledge. We are going to develop an LCA, LCC, and social LCA pre and post SIMBA project, and we are defining 2 policy briefs. Moving to the next one, you can see other outcomes. One is the roadmap to setting up new synergies with the ongoing initiative and among stakeholders. We are working to set of a criteria of select industrial symbiosis hub for replicability. We are working to define a SIMBA waste relation regional map, and we are also developing synergies and cooperation with the existing project and initiatives and innovative circular business model and post-project roadmap to be sure about the life after the end of the project. In terms of number, we expect a reduction of 76% of waste used as secondary raw material, the 58% gains in productivity from waste recovery, and the 13% beyond energy efficiency and CO2 emission. We have also defined an advisory board. We have 9 experts, and we are speak with them every 6 months or year in order to understand if the action that we are developing are in line with the market and with the market needs. And the exchange with them is extremely relevant and important for the next phase of the project. So moving to the next one.
I think this is the final slide of the presentation.
Yeah. Okay. Yes. So I repeat, in the first slide, you can find all our contacts. You can find all our social media channels. You can follow us and keep it always up to date in order to receive the development of this information. I would like also underline, just to concrete, I would like to use this opportunity also to create new cooperation for the future. There are a lot of interesting partners around this digital table, and Oscar, thanks a lot for the great work done. And I suppose that we need to use this type of round table and webinar to increase the cooperation between us and to develop new initiatives.
Yeah, for sure, Marco, and thank you very much for your presentation. And starting from this webinar, so we are able to identify some new opportunities to collaborate or even some synergies between some projects that are currently running, or even some proposals that are being built for new calls and topics. So thank you again for your presentation and participation in our webinar.
Thanks to you for the opportunity.
So now we will close the session focused on industrial urban symbiosis with sim sites, with a journey towards the circular economy. Will be a presentation that will be released by Emma Perez from ITEC. So Emma, it's your turn. Thank you.
Thanks a lot, Oscar, and also thanks a lot Life POLITEX and Life ANHIDRA for inviting me to present the SimSite project. I want to share my screen. No, pero esta no es. Esta no es. now everything is ready. So first of all, I would like to introduce the concept of industrial urban symbiosis, but I know that you already know because of the previous presentation. Wastewater and municipal solid waste volume coming from domestic activities is dramatically increasing due to the increment in worldwide population and activities in urban areas. Water pollution and overproduction of waste, which lead to shortages in natural resources, require innovations in waste treatments. These innovations must be based on a new paradigm, from waste management to a resource management philosophy. Through energy and material retrieval, wastes are considered to be a resource that can and must be drawn upon, which is the concept of waste recovery. Industrial and urban symbiosis is one of the solutions in line with the previous statements. Industrial-urban symbiosis is a strategic way of working to increase resource productivity through collaboration. The strategy is based on a long-term collaboration between different actors and sectors that increase the value of underutilized resources and promote environmental innovation. Industrial-urban symbiosis improves the competitiveness of companies and reduces emission and the use of primary and fossil resources, while strengthening regional development and resource security. Synside solutions are highly relevant factors in industrial-urban symbiosis by transforming waste and byproducts into green value products. The Synside project is an European project that belongs to the Twin Transition Call. This project overall aims at developing new technologies and solutions based on the industrial-urban symbiosis concept for local and regional collaboration among diverse actors and sectors, improving the sustainability of the use of industrial and societal resources, starting from wastewater and waste materials. The project is based on the creation of 4 ecosites in 4 European countries that have implemented 4 demonstrators covering different sectors, geographical dimensions, socioeconomic aspects, and resources. One of them is the Danish ecosite, which is based on food companies, including local farmers and a brewery. The Austrian ecosite is based on the meat processing industry. The Spanish ecosite is based on the textile and cosmetic industry. And last but not least, the Greek ecosite is based on the olive oil pomace production and refinery industry. Now you would be wondering, what is an ecosite? An ecosite can be considered as a small town with different actors that contribute to its maintenance and economic development. It's a well-connected and interactive system where everyone has a specific role. Each ecosite is based on urban wastewater treatment plants, municipalities, industries, or agriculture entities, all located in the same region. In this context, they form a hub that collects wastewater, bio-waste, and non-recyclable wastes, generated by both urban and industrial environments. All ecosites consist of an anaerobic bioreactor and an absorption column. The treatment technologies have 2 feed tanks, one of them for the wastewater and the other one for the bio-waste, which are pumped into the anaerobic bioreactor that will produce biogas to be transformed into methane or hydrogen as an energy source. After the reactor, the advanced antifouling treated membranes separate sludge and water, which is directed to the absorption column to obtain reusable water. The pyrolysis of the non-recyclable wastes is performed in a parallel installation, and the char is activated, functionalized with lignin-based nanoparticles or with carbon dots, and sent to all the ecosites to feed the absorption column. To conclude, in each ecosite, a co-treatment is developed to generate clean water, energy, several upcycle side stream of products, such as biogas, as well as high-value products like platform molecule, fertilizer, polyhydroxyalkanoates, for the reuse in each specific region. From the global energy crisis perspective, it is necessary to implement more cost-effective and sustainable technologies to replace current aerobic processes that require considerable amount of energy for organic matter oxidation. In a conventional wastewater treatment plant, this energy demand accounts for more than 50% of the total energy consumption, and a large amount of poorly biodegradable biomass is produced. These drawbacks have increased interest in anaerobic systems, since they have the potential to be both net energy producers and allow nutrients to be recovered whilst reducing waste sludge production. Anaerobic treatment has a series of advantages. Minimum sludge production due to the low performance of anaerobic biomass, reducing management, stabilization, and final disposal cost, low energy demand, since it does not require aeration for the degradation of organic matter, recovery of energy in the form of methane, which can be used to cover the energy requirements of the process. There are also limitations in the process that reduce its efficiency. Anaerobic biomass presents slow growth compared to anaerobic biomass, which forces it to operate at high cell retention times. On the other hand, the high production of wastewater per inhabitant in most developed countries requires low hydraulic retention times, since the treatment flow rates are high. Therefore, large reactors need to be used to store these high flow rates long enough for the anaerobic biomass growth. The other drawback is the low efficiency in the separation of the biomass. Physical separation by sedimentation is complex compared to the aerobic treatments, because the anaerobic sludge flocks are smaller and therefore their sedimentation speed is lower. As can be seen in this figure, the number of annual publications regarding the topics of anaerobic bioreactor alone and the combination of anaerobic bioreactor and municipal wastewater have continually increased over the time during the period from 2000 to 2019. In addition, the number of scientific publications focused on anaerobic bioreactor treatment of municipal wastewater went up suddenly in 2009. And in the following decade, the number of publications increased by a factor of 3, indicating that a steady increase in the attention paid to the anaerobic bioreactor for the treatment of municipal wastewater. However, the percentages of anaerobic bioreactor treating municipal wastewater among all the publications published about the anaerobic bioreactor accounted for 31% on any given year in the past decade. From these results, anaerobic bioreactors are also attractive options in the treatment of other waste streams, like industrial wastewater or organic solid wastes. The following table provides an overview of the effluent quality in different anaerobic bioreactor systems, as well as a biogas and sludge composition. The high quality of the anaerobic effluent makes this stream interesting for reuse in irrigation and fertigation. Hydrogen production from methane will guarantee a positive carbon footprint. And membrane technology can be used to concentrate or recover nutrients for the anaerobic effluents. For instance, hollow fiber membrane contractors is highly selective on nitrogen or phosphorus and can replenish a biofertilizer resource. There are key challenges that limit the applicability of anaerobic technology to municipal wastewater treatments. Among them, we can say that dissolved methane losses through the effluents reduce the energy recovery and especially increase the greenhouse gas emissions. Membrane fouling, which reduces system productivity and increases the cleaning requirements. And the pore size of the membrane is too large to ensure that viruses are excluded, which finally affects overall resource recovery. Among the innovation challenges in SIM sites projects can be highlighted. co-digestion of the municipal fraction of organic waste to significantly enhance organic carbon use, charge from pyrolyzed non-recyclable wastes for the absorption column, and methane reforming to hydrogen production. SIMSITES also proposed to fouling mitigation using novel configuration based on two different aspects, such as anti-fouling membranes based on metallocene nanoparticles and carbon dust coated to the membrane surfaces. This will be tested in the Danish, Greek, and Austrian ecosite, and a magnetically induced membrane vibration, which will be tested in the Spanish ecosite. Finally, I would like to highlight that the SIMSITES consortium is based on the work of 31 partners and represents academic institutions, policymakers, and industry from 8 European countries and Israel. And that's all from my side.
Thank you very much, Emma, for the presentation. And another example of how the industrial areas are also collaborating with the urban ones in order to take profit from different waste streams and valorization of this kind of waste and streams to take profit and to produce new raw material for different purposes. So for now, we are closing the seminar with the block 3 of our webinar, which is focused on the valorization of waste streams to obtain energy and new resources. Two presentations will be released here. The first one will be released by Laura Grima from IDIME. It is going to introduce all of us the live waste to coag project, so the brine metal waste valorization to produce coagulants for waste water treatment. So Laura, please.
Hello. Hi, Oscar. I'm going to share my screen. Hi. Let me know. Okay, pantalla. Hi. Can you see my presentation? It's a bit slow, the computer.
Yeah, it's in full screen. Thank you.
Okay, thank you. I'm Laura from IDIME, and I'm going to present the brine and metal waste valorization to produce coagulants for wastewater treatment. First, I wanted to say that we are 5 partners from different countries, and Global Omnium is the coordinator of the project, and he leads the validation of the technology in the urban wastewater treatment plant. Then we have Joviar and Aquafin, who are responsible of the replicability and the transferability of the technology, both in the industrial and other water treatment plant. Then we have AEL, who is in charge of the communication and dissemination activity. And then it's us, IDIME, who are in charge of the technical part, that is the design and operation and optimization of the demo plant. And also we are in charge of the environmental and the socioeconomic study. The project is expected to end by the next year, more or less. So we still have one more year to work. Okay, this is super slow. Okay, what is our problem to solve? We have 3 main issues in our case. First, we have the brines. There is a high generation of brines worldwide, which come mostly from desalination plants, and they are normally discharged without treatment, which has a harmful environmental impact because of the increase of salinity in the ecosystems. Then we have the metals. There is a scarcity of resources which, combined with the political instability, results in an increase of prices of everything. You can see below the increase on the aluminium prices over the years, and we have the peak in the pandemics and the peak in the Ukrainian war. Finally, we have the problem of the coagulants, that there is a high consumption, both in the urban and industrial wastewater treatment plants, and they are normally outsourced with continuous price increments, and these prices and the consumption is expected to increase because of the strict requirements in the effluent concentrations. So the key here is to valorize these wastes into reagents, which are the coagulants. But how do we transform these brines and these scrap metals into coagulants? Well, our solution is based on the electrolysis, where we apply a continuous electrical current to cause a non-spontaneous chemical change. And depending on the metal that we use as the anode, which is the sacrificial electrode, we will have a substitute of the commercial iron chloride if we use steel as anode, and a substitute of the PAC if we use an aluminum anode. As an advantage from our side is that we are using brines as the electrolyte of the reaction, which has a high conductivity, so they allow the application of lower voltages, and that means that the consumption, the electrical consumption, is lower than conventional electrolysis and electrocoagulation. From our point of view, this solution is a multi-sector approach, the live waste to coax solution, because all the different streams belong to different industries. As you know, the main objective of the project is to generate high-quality coagulants that can be used in wastewater treatment plants. And these coagulants are based on the brines that we receive both from industrial plants and desalination plants. And we are also using the scrap metals that comes from the metal industry. Everything here is transformed through the electrolytic system that we have developed, but this is not the same as the electrocoagulation, as we have said. Okay. To start with the technical overview, as you may know, the coagulation is a water treatment where we destabilize the polluting particles contained in the water, so these particles can settle and we can remove them from the water. In the conventional coagulation, we do that by the addition of chemical reagents, and in the electrocoagulation, we do that by the addition of an electrical current. So we generate the active species on the surface on the anode, and we can control the generation of this reagent. In this case, can be the aluminum or the iron, if we use the aluminum or the steel. But this is the conventional electrocoagulation, and in our project we are using the ELS system, which is the electrolytic system. And what are the difference and the advantages of our project and our process with the conventional electrocoagulation? Then we are going to see them here. We have that the objective is different. Okay, in the conventional electrocoagulation, the main objective is to treat wastewater. And in our ELS system, the objective is to produce coagulants and valorize wastes, as we have seen, the scrap metals and the brines. As for the electrodes, in the electrocoagulation, the electrodes are commercial ones, but we have to use the metal scraps, which are cheaper because they are a scrap, they are a waste, and it's good for the environment because we are valorizing this waste. Next, with the electrolyte, in the conventional electrocoagulation, it is the wastewater that you want to treat, that you want to remove the pollutants. And in our case, we have the brines that have the high conductivity, which is good because it's a lower power consumption. And on the other hand, it's good for the environment as well because we prevent them from being released to the ecosystems. As for the versatility, the electrocoagulation is very standard. And with the ELS, we have to work with a wide range of qualities, both from the metal scraps and from the brines that we receive of different types. And there is also a versatility on the quality of the products because we have to deliver high quality coagulants for very different end users. So we have to take into consideration what the client needs. Okay. As for the similarity, they are both easy to operate because the process can be controlled with a power source, and you can control the level of the coagulation that you produce using a rectifier. And then in both of them, there is no need of reagents That means that you produce a less volume of sludge that then you have to manage, so it is good for the companies. And also you don't have to store the chemical reagents, which is also sometimes it is unsafe. As for the benefits of our system compared to the conventional electrocoagulation, we have that the product that we obtain from the ELS can be commercialized, so it's an increase of okay, you can sell it, and the waste valorization that we are valorizing both the brines and the metals. In the end, the power consumption is lower in our case because of the higher conductivity of the brines, as we have explained before. Okay. This year we have already the results of the industrial water treatment plant, and we wanted to share with you the results of the validation because they were really good. So in our case, we did the transferability of the technology in an industrial company where the brines came from the mineralization equipment. So because they use this equipment to obtain their processed water. And as you know, when these columns are clean, they are clean in different stages. And what we did with these stages is to separate the streams of each one and prepare the optimum mixtures to feed the electrolytic systems. So the brines coming from the demineralization equipment were fed to the ELS. So after feeding the brines to the ELS, we obtained both the iron and the aluminum coagulants, and we could valorize up to 70% of all the brines that were generated in the industry. So that was also a saving for the company. They could save the management of those brines. As for the coagulants that we produced in the pilot, they were used in the water treatment plant as a substitute of their conventional coagulant. And you can see here the results that the removal yield, the average removal yield was pretty good, over the 90% of removal in all the heavy metals. And also, as for all the parameters, including pH and conductivity, were within the legal limits of discharge. So there is a purification efficiency comparable to conventional coagulants, which is pretty good and successful results. So as conclusions, we have seen the problems tackled in this project, which are the brines and the metals and the high consumption of coagulants. How did we valorize this waste into the reagents? The overview of the electrolytic system and the successful industrial validation. So to finish, I wanted to say that we are open to collaborate, and we welcome your wastewater and your brines to test them in our demo site. So feel free to contact us if you are interested or if you have any kind of questions. Thank you for listening, and I hope this was interesting and useful. Okay, let's see if I can stop.
Thank you. Thank you, Laura, for this nice presentation and a nice example of how to manage some wastes, to take profit of them, and how to transform this kind of wastes on raw materials for new processes. So now we are going to provide another example of how to take profits from some wastes. In this case, this kind of wastes are cellulosic fibers that are released by a closed loop system, a closed loop water treatment system, which is the ANHIDRA system. Victoria Reyes from ITEX is going to provide you some results of these live projects, mainly based on valorization of cellulosic waste. So, Victor, the floor is yours.
Thank you, Oscar. I will share my presentation. Yeah, hope it's working. Okay, so now it's my turn to close up this session about the valorization of waste streams. And I will talk about how we've worked in the Life ANHIDRA project about the valorization of a cellulosic waste we've obtained from the ANHIDRA's water treatment loop that we've developed within this project. I'm Victor Herraiz from ITEX, and I will briefly go through all this project. So the consortium that sets this project up is based in the Iberian Peninsula in Portugal and Spain. Pizarro is a textile finish company. Genealogia is a company that makes eco-friendly technologies for the textile industry, and we at ITEX are the Textile Research Institute of Spain, and we have either laboratory services and R&D projects. So the first partner is Pizarro. They're a textile finishing company that makes all of the process necessary to take a garment from from factories to stores, and they work with a lot of international brands. And one of the products that they work with a lot it's denim. And so, you know, denim is quite a different textile because it has its own processes, because the denim look that we all seek for, it's pretty different than the other garments. And for that, you need these processes you can see are performed in industrial washing machines, and then they use a lot of water and then a lot of chemicals so they can get the looks of the denim. So what we are doing in this project, we've done in this project, is to implement a water regeneration loop within the facilities of Pizarro. And what the objective is to take the water that is taken out of the washing machines, treat it, and then use that water again to treat new garments. So it's a closed loop of water. First results of the life cycle assessments has lead us to a savings of 92% of the water inlet, also a 98% of water discharge. And as indicators of global warming power, we have a 44% saving, and also in water deprivation and 85%. So how this system works, we have washing machines that are the conventional ones of the factory that produce wastewater. We take that wastewater and pre-filter it. We remove fibers and parts that are removed during the system. Then we treat it with ozone so we can remove any organic material or colorants in this case, and also an ultrafiltration step that we find the water. So we store that water in a buffer tank so it's ready to use it again in the washing machines. So one of the downstreams that we get from this treatment system, it's fiber waste that is from all of the garments that with the abrasion of the stones and the oxidants that we put in, we get this with waste, which is mainly composed of cellulose, but it also has other impurities such as stones on the stone washing treatment, and other metallic parts that can be on the jeans or in the jackets that have been treated. So in this stage, we collect many different wastes depending on which filter we take them in. So for instance, in the pre-filtered, it's a more coarse waste with more big particles. In the first filter, we now get a more smaller fibers. And in the last filter, we get a even smaller fiber size. But the particularity of this waste is pretty heterogeneous, so it's kind of hard to work with. So how have we worked with this residue in the ANHIDRA project? And we've considered mainly three valorization routes. The first one is to transform this waste into a pigment so we can apply it in a textile traditional processes. The second one will be an energy valorization of this waste through anaerobic digestion. So we generate methane that can be then transformed into into energy. And then lastly, some other routes that we explore but are considered low value articles. So for the site reducing process, we've taken the dried fiber waste we obtained from the ANHIDRA system. Then we have two options: just put them in a steerable mill, and we get a 55% particle size reduction, or we've tested a wet process where we put the fiber in a water suspension, then steerable mill it, and then we get this slurry that we can spray dry, and then we get a powder with a 90% smaller size distribution. Then it's similar to conventional pigments, so we can apply it as in traditional dyeing or printing routes. So for pigment dyeing, we've worked mainly with cotton substrates. So we had to pre-treat these fabrics with, in this case, we use an ammonium quaternate polymer. So this fabric can bind with the pigment, and then we can dye fabrics, and we get these distressed looks that can be put into the market. Another valorization route is the coating or printing. So we use this pigment in a printing paste. So we need a binder and also a thickener agent, and then we apply it in a coating process or in a screen printing process. Here you can see some of the prototype we've developed within the project. On the left, you can see dye garments. We have some jeans, or we have some bodysuits. And on the right side, you can see some printings with the project logo. And also we've tested the laser technology into this pigment, and we've seen that it also works with it. So with this solution, we get a circular value close of the chain. So we are introducing the textile waste again into the textile industry. Next one will be the valorization, energy valorization of this waste. In this case, we've done biochemical methane production test that measures how much methane can the bacteria generates from this waste. And in this test, we put in contact a wastewater treatment plant inoculum, which has many methanogenic bacteria in it. And we feed this bacteria with the cellulosic waste we get from our system. And we've seen that with this waste, bacteria increase their methane production. So we know we can use this substrate as a energy valorization route. Lastly, other route we have considered are for example, the clothes hanger you can see on the slide, made by hot press plates technology. You can get these considerable value materials. Also, you can create with laid non-wovens that can be used, for example, for composites reinforcement. And lastly, with this cellulose-rich waste, we can create new man-made yarns, as in cellulose-based yarn, that can also be reintroduced into the textile industry. And that be all from my side. If you have any questions, you can contact us, and thank you for attention, not only to this presentation, but for the webinar with hosting. Thank you.
Thank you very much, Victor, for the presentation. And regarding ANHIDRA, I want to take the opportunity to congratulate all the ITEX staff involved in this project, working very well with the partner Genealogia and Pizarro in order to ensure the success of the project. So we hope we will see very soon these results on the market, on a sector, textile industry and textile processes, that are like a predator of water It's a very intensive water industry, and this kind of project and technology can help to save significant amounts of water. Also, with this point of view of the circular economy related to fiber waste valorization. So this is the end of the webinar. Hope all of you enjoy about the presentations, find some inspiration for new projects and new proposals. And also we will upload the presentations and also the recorded video of the webinar to our social media channels, to Live POLITEX and Live ANHIDRA channels. So stay tuned in this social media. Very good luck to all the projects to ensure the smooth implementation and good results. And that's all. Thank you very much and have a nice day.
Thank you. Bye.